Welcome to Papers We Love 17. Woo! Yes, I don't know why, I just always like to woo. So, I don't know how many of you are new today. I'm seeing some new faces. Can you, one? Ah, nice. Oh, awesome. All right, so we've been around for a little bit over a year. The goal of this group, if you don't know, is to bring academic research closer to practitioners. And since January, we started breaking our meetings into two sections. We have a mini that is 10 to 15 minutes with some questions, and then we have a full-length talk. So normally, I will have food, maybe a little break, maybe I will say that it's 2 minutes, but in all reality, maybe a minute and a half because time is really weird for me. So our mini today, so we have two speakers today, Kelsey and Ben. So our mini today deals with information escrows, and Kelsey is going to be our first speaker. I tend to introduce the speakers with their bio and something fake about them, like put in the middle. So hopefully you'll be able to figure out what it is. So I'm going to read you about what Kelsey's bios. Kelsey is the Director of Technology at Sexual Health Innovations, where they're currently building Callisto, based on Ayers and, I don't really know his last name, Unkovich's paper. She'll be talking about the joys and pitfall of going from academic paper to production code, which should ring familiar whether your source is Microsoft Research or the Michigan Law Review. In her spare time, she is an aspiring tattoo artist with a specialty on toy dog breeds. So if you need a toy dog breed tattoo, Kelsey is your person. So let's give it up for Kelsey.
Okay, cool. Hi, my name is Kelsey Gilmore-Innes. I'm the Director of Technology at Sexual Health Innovations. We're a nonprofit devoted to building tech to further sexual health and well-being in the United States. We are currently working very feverishly on building and delivering Callisto, which is an online sexual assault reporting system for college campuses. It's designed to be confidential, secure, and survivor-focused. We're rolling it out at 2 colleges this fall for freshman orientation, which is very, very, very soon. And it's designed to be an interface to existing Title IX reporting systems. We're taking an existing process and putting it online. We're also introducing a new idea that comes out of this academic paper, which is why I'm here talking to you at Papers We Love. So information escrows is a concept introduced in the title of a 2012 Michigan Law Review article by Ian Ayers, who's an economist and a professor at Yale Law School, and Kate Unkovich, who is a grad student at UC Berkeley. An escrow is a system designed for 2 parties who are undergoing a transaction to put some third material with a trusted third party, and it's released under conditions agreed to by both of them. The concept of information escrows is sort of a newer thing. There's a couple different kinds that actually already exist. One is called a commitment escrow, which the time I've most often seen it is like in crime movies where it's like someone witnesses someone committing a murder and they're like, wait, here's an incriminating thing about me, don't kill me. And actually game theorists write papers about this, which is funny. There's also a concept of a posthumous escrow, which is the idea of an escrow where information is released after the death of a person or an institution. So one form that this takes that you may have encountered is a software escrow where a company will put their source code in escrow with a licensing company, and if the software company dissolves, that source code is released. Another one that's much more common is a shared interest escrow, and there's a couple of different common actual applications of this. Negotiation and auctions, actually, they've experimented with doing an escrow system where both parties will put in a range of acceptable offers, and the third party will only release the bids if they overlap in some way. Dating escrows, actually. So if you ever, in the early days of Facebook, used, Find My Crush, and you put in, 6 people you have a crush in, and if any of them put your name in, then, they hook you up, which is kind of like Tinder. So in some ways, Tinder is a shared interest escrow, although not actually cited, sadly, in this paper. Adoption, actually, they've been exploring information escrows as a way in closed adoption states to connect birth parents and adopted children. Adult adopted children. And the 4th category is allegation escrows, which is what the subject of this paper is about. An allegation escrow is an escrow that holds claims about a crime. And the claims are only released or really filed if a pre-specified number of claims are all filed against the same defendant. And we're incorporating this into Callisto when talking about sexual assault. So we have an option in Callisto where you can choose to put your report in escrow and only have it filed to the school if someone else files a report with the same assailant. And the reason why this is a useful concept is this game theory concept of first mover disadvantage. And that's when being the first person to make an allegation holds some sort of disadvantage. And so in the case of sexual harassment and sexual assault, fear of retaliation is a big one. It's not so much in those shared interest escrows, we see sort of like a fear of lack of interest on the other part. But here the fear is retaliation from parties not involved in the escrow. Sadly common sort of strategy when people are defending against claims of harassment or assault is branded a nut or a slut strategy, where the accuser is cast as either someone who is mentally ill or has brought it upon themselves by being slutty. Another reason why there might be reasonable fear of retaliation in a sexual assault or sexual harassment scenario is that many harassers and rapists prey on vulnerable people. So the concept being that they've picked out someone who is particularly vulnerable to retaliation or threats of retaliation, which is the reason why you would see a disadvantage in being the first mover. It's kind of a he said, she said thing. We see this in the Cosby case, which was a big deal in the news recently. Being the first person to come out with a claim of sexual assault is not a fun position to be in. There's another way that there's a first mover disadvantage when you're talking about assault and harassment, and that is wrongdoing uncertainty. So people like to talk about how there are gray areas with assault and harassment. I am not convinced there's as many as everyone likes to claim, but I think there are some gray areas where, especially considering sort of some of the cultural influences, a victim isn't sure if they've been assaulted or harassed. And in a lot of cases, predators really thrive in that area. It can create an avenue to open up an assault or an instance of harassment if you know that the person you're sort of attacking isn't going to be able to really claim with certainty that something bad happened to them. This sort of brings these kind of assaults into a category in game theory that's called a stag hunt problem. Game theory really likes animals. It's also called a penguin problem. The basic idea there is where group action together would get you a better outcome for the group, right? But acting rationally as individuals without cooperation, individuals end up taking a less optimal action. It's exacerbated here by not knowing who the other victims are, or even if they exist. So the idea of an information escrow is to reduce that first mover disadvantage. The problem is, though, right, that you want to reduce the first mover disadvantage, but there's also a concern that if you offer a way for people to file complaints that never actually get seen by the appropriate authorities, you could actually reduce reporting in general. If you end up with a lot of what we call orphaned complaints, which are complaints that go into the escrow but are never matched, you could end up with a lower rate of reporting, which is not exactly what the system's designed to do. So what this paper sets out to do is to model sort of what would happen if you introduced escrow into these reporting systems. And so it sets us up with some variables. This reflects, they're up here, it's basically, you have probability variables, right? But the ones that we're concerned about is what is the probability that a victim of a crime that you have an escrow with will file a direct claim without the escrow, right? And then what's the probability that someone who suffers from this first mover disadvantage would actually file a claim if someone else had already gone? This model reflects a couple of things that we know about claimants in crimes like these. One is that the first probability here, the PD, is less than 1. We know that not everyone is willing to file direct claims. The second one we know is more than 0 because we've seen this over and over again in cases where someone will go public, will risk that first mover disadvantage, and it'll turn out that there were other victims along sometimes, months or years that also now are willing to come forward. In order to model how an escrow would change the situation, you need a couple other variables. These two variables are to model the effect of it. It's saying, well, okay, how many victims would have filed despite the first mover disadvantage, but now with the availability of an escrow, will escrow instead? And then how many victims will put their claims into the escrow instead of just not filing at all? There's also another variable, which is how many claims you have to get to trigger it, but basically all the modeling indicated that 2 was probably optimal, so I've kind of dropped it in this, but that's also a variable. So the question comes up, what numbers do you put in here, right? And like the answer to that is kind of like we don't know. Especially when you're studying underreporting, like it's in the name, it's hard to study, right? So what Ayers and Unkovich did was I'm not being detrimental when I say this, they made it up, right? They asked around, they did some surveys, they looked at some existing studies, and they came up with some reasonable numbers to put in there, and they modeled it. And so if you have numbers that you can put in here, you can model what the effect is. So for example, this table, which is hard to read, and you don't need to read anyway, don't bother squinting, don't hurt your eyesight, is basically talking about a scenario where only 10% of victims will ever report, and 20% of the remaining will come forward if there's another report. It picked 5% that would escrow instead of direct reporting, and 15% would escrow over silence. Again, these are sort of arbitrary. And then it models what would happen based on various numbers of repeat offenders in this case. We see improvements here, especially for those repeat offenders. We see improvements on the lines of 15 to 20%, which is really significant. Again, these were arbitrarily chosen, right? It's speculative at best. But what's interesting about this, right, is you can actually take this and you can plug all different models in there for this simulation. And what you can do is come back and look at the results and use that to back model and be like, what kind of conditions are good for an escrow and what kind of conditions aren't? And we sort of, here's one of the tables, there's a couple tables in the paper like this, right, where they show you combinations of different models. And they've released the data and you can go plug it into an Excel spreadsheet. One of the big conclusions here is that underreporting is a huge factor in this. Problems where you have severe underreporting are gonna actually be really benefited by an escrow situation being available. These are the ideal escrow conditions when we look at those variables we modeled. If you have, like I said, if you have an underreporting problem, if there's a lower probability that people will make direct complaints, that lends itself to an escrow. If you have a high, if you think that there won't be a ton of conversions from direct to escrow, that's probably better for the escrow situation if the endpoint is getting more folks investigated. Similarly, if you think more people will be willing to put their reports into the escrow who wouldn't have reported in any way before, that also helps. And we tend to think for sexual assault on a college campus, both of these are true because of the sort of shame around it and the very public and negative consequences that public accusers face. Another one is, this really works best if you have a high probability of multiple harassers, right? Like if you have a crime that you know people are gonna repeat, this escrow works really well. So there's good reason to think that sexual assault in college is a crime that has a high probability of multiple assailants. There's a study in 2002 by David Lisak, which found, in his study, he found that about of the 6% or so of men out of a large college sample who admitted to rape or attempted rape, a startling 63% reported committing more than one. And they actually, of those repeat harassers, those repeat assailants, they reported an average of 6 assault acts each. So that's a really like striking result, right? So here's where I come in with the stuff that's relevant to all of you as computer scientists who implement papers. So benchmarking is really hard, and you may have noticed this in the news last week, at least a lot of people sent it to me. There's a study that came out last week that actually gave really different answers than David Lisak's study and said, well, actually, when we look at it, most of the rapes aren't committed by serial rapists. So that's interesting. If you look at them, they use a different definition of rape. They survey a different college population. One of them was Boston Commuter College students. Another one was a Southern residential college with a large residential population. This new study counts everything within a year as one instance. It also studies only sexual assault, where the earlier Lisak study looked at a bunch of different instances of interpersonal violence. And specifically what the results challenge is the idea that repeat offenders show like a stable and high rate of perpetration over time. They didn't find that in their new study. So which one's right? Yeah, if you've ever done a benchmark, you know that the answer is like shrug emoticon. This scale is really important. Having a baseline is really important. the definition of what you're measuring is really important when you run a benchmark. And these are all, and I don't want to say easily manipulated because I think that imputes too much intent into what's going on. They're just hard to measure. It's hard to measure. And in some ways, we have it easier in implementing Callisto when we look at these numbers because we at least have the advantage that our measurements are made on real life systems, which for a lot of academic papers, that's not the case and it won't be for a long time, especially when you're looking at things that are intended to be implemented at large scale. In a lot of ways, this is a project of measurement. We are interested if the results in this paper bear out, but we don't know if they will. And there's so many unanswered questions about college sexual assault that we're building a system that is in and of itself a really important opportunity to get new numbers on it. So let's say that this new study is right, and we have a really low number of repeat predators, repeat assailants. Well, thankfully, in the paper, they actually go on, after those tables that I showed you, to talk about other costs and benefits of implementing an escrow. And they're actually talking specifically about sexual harassment on college campuses, but we believe that these all apply to assault as well. The benefits are claim selection. So there's some, it's not really necessary, there's not one crime here, right? Like there's a lot of different ways that assault looks on a college campus. So the thought is that more blatant crimes will be more likely to be directly reported, but we'll see sort of a triaging and a surfacing of repeat offenders who are doing that sort of uncertainty thing I was talking about. One thing that we think is a huge benefit, it offers a single venue for reporting. So students can report an assault directly. They don't need to go into the escrow, and they can report an assault directly through Callisto. And I don't know when the last time any of you have been on a college website before, but we actually think this is a huge value add in and of itself. It's really hard to find the information about what resources are available and how to report on any given college website. Another one is that the escrow allows people to record evidence close to the event and store it while they go through the process of deciding if they want to take on that first mover disadvantage. And one of the schools we talked to, they reported an average of at best 6 months between assault and the victim's first contact with the college Title IX office. So that's a huge gap, and just in terms of memory and trauma and treatment, it's so much better to get that stuff down immediately, so that's a good, important benefit. In terms of costs, you have an imbalance of staleness. All those things I just said, we offer to the survivors, and the defendants, the people who are accused, don't have that. There is the danger that we will end up with implementing an escrow giving less weight to uncorroborated claims, and they describe this in the paper as the 2-bite rule, where you can harass or assault someone once and you'll get away with it because you have to have 2 claims to actually get anyone investigated. That would be a bad thing. Another one that they talk about is false and bad faith complaints. And I really wanted to point this out because I thought this was really interesting. In fact, I would say about half of the paper by page is about bad faith complaints, which is, I think, a glaring difference between a law paper and a computer science paper. And this, again, if anyone who's implemented anything will agree, right? Like certain things like security, right? Or bad actors are very rarely sort of emphasized. And I think that was really interesting and really helpful that someone had already really systematically thought through some of the risks and fail-safes you could put in to deal with bad faith actors, which is really cool and helpful to us. So the last thing I'm going to talk about is the concept of spherical cows. This is like a joke from physics where if you ask a physicist to give you a real world answer to anything, they'll be like, well, assume a spherical cow. There's a lot of assumptions built into this paper, right? There's a lot of assumptions built into any paper that's talking about anything. One thing that's kind of nice is they actually laid out in this paper what some of those assumptions were. Some of them were that accusations were publicized when they were calculating those probabilities between the first round of acting and the second round of acting. Another one is that they just assumed, they didn't build false claims into their calculations when they were doing statistical analysis. Another one that they pointed out, which is interesting, is they assumed when they were comparing the two that the likelihood of offenses were the same. But I mean, our goal in building this and in trying to improve the reporting process for college sexual assault is to make a change in behavior, right? Like knowing that there's this system and that there's support and that there's strong consequences for assault should change the likelihood of offenses. There's also a couple that we've run into that weren't in the paper, which also will probably be a familiar situation for folks who've implemented things. One is that in the paper, they assume that reporting in the escrow is automatically triggered no matter how long the length of time is between a report and a trigger, and that the school's notified first. And this runs into all sorts of squeaky, weird consent issues, which you really don't want to mess with when you're talking about people who've survived assault. Another one is it's like assume a perfect matching algorithm, which is rough actually, and it's an open question for us what information people do know about their assailants and what unique information people do know. I went to a school with 50,000 students. I think there were 4 Bobby Lees in my chemistry class alone. We're matching on name isn't really gonna work. Actually, yeah, we looked up some common names to sort of prove this point. So we have to figure out a unique ID that people can use that doesn't fall afoul of laws about releasing student information. So that one's been a difficult one. A third one that's really interesting and that I already kind of talked about is that the escrow agent is unimpeachable. That's both that, and I mean that on a couple levels. One, I mean on a basic security level, and I think again this is going to be common when you're implementing anything. We very rarely handle security first when we're talking about implementing systems, but it's drastically important. Another one is, for example, when you're filing information with a third party, and then there's a court case about it, we now have a attacker in the sense of information security, which we can't reasonably put up technical defenses against necessarily if we get subpoenaed. And that one has been tricky and interesting, and I'm actually really excited about the solution we've come up to. It's kind of the part of this system that has fun cryptographic implications, and if you want to come talk to me after, I'm happy to chew your ear off about it. But that was definitely a spherical cow that was assumed in the paper that we can't really sort of bear out. So to conclude, they finished the paper up by talking about applications. Some of the ones we're excited about, non-college environments, the military is obviously a very interesting one. It's where this issue is very important. Sexual harassment in the workplace, that one's interesting too. How does college is nice because it's a constrained environment. You have people who are in the same place for the same time, for a constrained amount of time. Workplace isn't as true. Whistleblowing is one where there's obviously a first mover disadvantage. Adverse drug events is interesting because there's not much incentive, and Ian Ayres, who was the professor who wrote this paper, studies incentives, and there's not much real good incentives for doctors to report drug events, so he had some interesting thoughts about this. The spherical cow stuff that we start to get into, these last two are really interesting. One of them proposed is a suspicion escrow for adultery. So if multiple people suspect that your spouse is adulterous, they could file it somewhere and then you could be notified? Yeah, that is like a 5-dimensional spherical cow to me, but that idea is interesting. And insecurity escrows, for example, if you were concerned that your breath smelled or your talk was boring, you might use some system to get, if one person says my talk was boring, they're just petty, but if all of you think it was boring, then I want to know. So that's just some thoughts. Anyway, thank you for listening. You can check out more about the project at projectcallisto.org, and I am super happy and excited to talk about technical stuff with folks about it anytime.
I think we probably have time for 1 or 2 questions.
Does anybody have any questions?
When people report the assault or whatever happens, do they report it anonymously or with their full information?
That is a great question. It is a confidential but not an anonymous system, which is pretty important, right? Because, all of that first mover disadvantage stuff has to do with people making reports under their own name, but this is a system for people to make reports under their own name.
Okay, and then second question, when let's say 2 people accuse the same person of something, can you go into more detail of who gets notified, what information, and so forth?
Sure, so the paper actually talks about this. It's sort of part of that bad actor section as well. Ideally, from a game theory standpoint, you want both reports to go immediately. It turns out, there's a lot of consent issues about that, right? It's not really an ideal situation for anyone, for someone to get a phone call out of the blue to be like, I just got this report about something that happened to you a year ago. Also, security-wise, that means us hanging on to decryptable information that's really pretty sensitive. So we have sort of... We've come up with a compromise. I was going to say we've cut the baby in half, but that's not really fair to us. We've come up with a compromise where the school is notified that reports have been made about this person, and they're given the contact information of the people who are reporting. But the control over the actual account of what happened, that control always belongs to the survivor, and that's a really important principle of what we're doing. And I'm not going to talk about it now, but we can talk about it after. There's all sorts of interesting legal and jurisdictional implications of what a school is compelled to do if they have reason to believe that there's a serial perpetrator going around. So, yeah.
Any more questions? Nope. Oh.
Hi, Jordan.
Hi, Kelsey. Great talk. So I guess going with the whole theme of like implementing this paper versus implementing an academic paper, and sort of following up on that question, in the same way that like a database paper tells you how to build a database but doesn't tell you the interface, how do you like figure out how to actually like someone comes on board, you need this information. I mean, it's kind of the same like, right, like typical funnel problem, but a bit harder.
Yeah, and actually, I feel like it's a whole other conference talk that I hope that my coworkers do about the interface to the system. The designer and the project manager working with me have done some really interesting work on trauma-informed design and interview design. So these are sort of fields in and of their own right. And I think that, look, there's a reason why we did this, right? It's not just the information escrows. We all live on the internet, and college students even more so live on the internet. And we do a lot of our day-to-day life, both good and bad, on the internet. And figuring out interfaces for traumatic situations or sensitive situations, situations where security is paramount, situations where people could potentially be re-traumatized in a really dramatic way. It's a brave new world, and there's a lot of interesting stuff. Jordan and I work together, and he knows that I am not a front end or UX expert. So I just take the mock-ups that I'm given and I'm blown away by them. But yeah, I hope that we will be coming to a conference near you soon talking about the UX of this, because it's super important. Thank you, guys.
All right. So this is our our big talk of the day. So here's Ben, and I'm going to read you his bio. Ben is a co-founder at Resonance Labs, a pre-launch company working to transform the way that developers build, understand, and interact with distributed systems. Prior to starting that company, Ben spent 9 years at Google, which he left as a senior staff engineering. During his tenure there, he led the design for several large distributed systems. The most significant of these were Dapper, which is an always-on distributed tracing system, which we covered in our very, very first Papers We Love, and Monarch, which is a highly available time series collection, storage, and query system. Both are important pieces of Google's production infrastructure today. But before that, Ben used to tame Arabian horses. So if you have any sort of questions, Ben is the person to ask as well. Give a round of applause for Ben.
Thank you, Inez. Can we also give a round of applause to Inez for organizing these things? Having been on this side of things, I can testify to the fact that it's actually a lot of work and pinging people like me who are being a flake and stuff like that. So thank you, Inez. All right, so I'm here to present Spanner, which was a paper that came out of Google and was presented at OSTI 2012. I am presenting this for two reasons. One is that I do love this paper, in a polyamorous sort of way. I love other papers as well, but I do love this paper. And also that I felt like I didn't really understand it when I read it, so maybe if I presented it, I'd have to, which has worked better than I was fearing, but I still may get some things wrong, who knows. Does anyone here work at Google? All right, cool. Well, if anyone hears me saying something that seems untrue, I welcome dissent always. And please interrupt me if you want to shout out a question. Oh yes, I hope the slide link gets shared at some point, but there's a link to the paper here as well as Great, as well as a link to Wilson Shea, who's much smarter than I am, who is giving the OSDI talk about Spanner. I also wanted to mention that his talk really focuses on true time specifically. That's where most of the emphasis is, and true time, as I'll get to, is probably the most important theoretical contribution of the Spanner paper. So if you want to hear about that in great detail, I'd recommend watching his talk. I will discuss it, and I can answer questions about it. And I decided instead to focus more on the big picture of, what are the things you should come away with if you want to sort of know about Spanner in general, and also the context at Google that caused it to come about in the first place and what the motivation was, because I don't feel like the paper had enough space to go into detail on that. All right. So in 2010, if you wanted to build something at Google, the actual list, of course, is much longer, but let's just break things down into these rough categories if you wanted to store and query things. There was Colossus, which was very similar to GFS or HDFS or whatever. People are familiar with that. Just a big distributed file system. The API was suitable for doing high throughput writes in append mode, and in certain contexts it might be appropriate to do reads, but for the most part it was really, really difficult to build actual applications on top of Colossus unless you had no choice. People were frustrated with GFS for similar reasons, which is why Bigtable was created. Bigtable, of course, started this whole NoSQL revolution. There's a great quote that I don't actually know well enough to repeat it verbatim, but the gist of it was, I think NoSQL is a really silly term, and the quote was taking the line that saying that something is a NoSQL database is like saying that whale meat is not ice cream, which I think is true. There are a lot of things that aren't SQL. They're not all the same. So what does that even mean? Anyway, but Bigtable started that trend, I think, and it was definitely an improvement over GFS in the sense that the read and write load was supported for many applications. The problem with Bigtable is the programming model is really unfriendly. It's very systemsy, and it's basically just a big key value store. So Megastore was a project that brought SQL-like semantics and APIs to a Bigtable backend, but it was implemented strictly as a public client to Bigtable, which basically means it's really slow. And if you're ever waiting for a Gmail message to load, it's probably at some level because of Megastore. And so it wasn't really good enough as a performer to replace the kind of last gasp of MySQL at Google, which is the ads database, which is this enormous, frightening, multi-headed, sharded MySQL monster. And obviously, given that it generates a disgusting amount of money, they kept it running, but it was terrifying. And, when they had to move the shards around and actually this is discussed in the Spanner paper, but if one shard is getting too big and MySQL is just going to run out of memory, even if Google bought the most expensive machine they could buy, you'd have to move these customers from this database to that database and so on and so forth, and just do a rebalancing of the shards. And so the last time Google ever did that took 2 years to reshard the MySQL databases. It's just astonishing cost, right? And this is really good people working on this insane stuff. So they would have moved Megastore, but from semantically it would have been better, but it was not nearly performant enough for what they needed. Hence the need for something like Spanner. And Dremel I'm putting on here just because Dremel was, which is similar to, it's one of these sort of column IO based things there's a lot of them out there right now, Impala, whatever. They have a really beautiful query interface in that it's SQL, and it turns out people really know and love SQL. It's been around for a really long time, and people are into it. And so I think the Spanner team realized that maybe they should make a more usable version of Bigtable. So that's that. So I've already addressed a lot of this stuff. The paper does discuss several things that people at Google wanted that they weren't getting. and those are at the top. The one thing that's not mentioned in the paper that I think is actually very important, I may be biased because the second project that I spent a lot of time on at Google is Monarch project. We had to monitor everything at Google and kind of be the last system standing except for the scheduling system. And that meant we couldn't depend on really anything. So it meant being distributed in every data center at Google. So we were particularly affected by this. But if you have a big service at Google, and so that's to say, you're in many data centers, not like 3 data centers or 5 data centers. There are these things called planned change requests, or PCRs, which are basically like, we need to upgrade all the motherboards in this entire data center. We're going to take it offline, upgrade them, then turn it back on. It takes, a couple days, whatever. Except that, of course, everything that's singly homed there needs to move somewhere else. And you do get plenty of notification about this, but these things are continuously happening. And if you run a service, you could spend an enormous amount of time dealing with these things. And if you were using Bigtable, or really just about anything, almost everything at Google is basically per data center at some level. And Spanner is incredibly ambitious to try and address that problem and be a truly global storage system. Like the Spanner universe, which is the top level element of the kind of Spanner system, is not regional, it's global. And to design a global storage system, given the various constraints that puts on things, is extremely ambitious. So Spanner, it's general purpose transactions. It has a SQL-like query language. It doesn't support all features of SQL, but it's reminiscent of it. The tables are schematized in a way that's kind of clever, which I'll discuss. The data model is kind of relational. It doesn't support secondary indices, so that eliminates a lot of things you would want to do with a relational data model. But and then the big feature that they get really excited about, for good reason, is externally consistent transactions, which I'll discuss in detail, so I won't talk about them now. So this is a chimera, and I think that Spanner in some ways is a chimera. It's just, and a chimera, for those of you who can't see, I guess, is an animal that's like multiple animals all at once. It's a little bit hard to know what Spanner is. Is it a key value store? Is it like sort of a SQL database? Is it this thing that actually provides reasonable read and write performance, which that alone is kind of exciting at scale? Is it something that gives you really fine-grained control over replication, which would be a kind of a cool feature? There's this distributed transactions thing, which is cool. Lock-free reads, which is really appealing. And of course, the answer is yes, it's all of those things. And that's a lot of stuff. And this paper is really, about, well, okay, so what's the trick? And that's what I'm here to try and summarize for all of you. The things that make this work, if you really kind of look at it from first principles, true time is definitely the biggest contribution of the paper, which I'll definitely talk about in more detail in this bullet. And another thing which is sort of hard to really pin down, but I don't know, it's sort of funny that the systems community got to claim systems to me. I mean, everything is a system, like there's like the water system, and I don't know why they get to call themselves systems, but I think we all know what it means when we say systems community. But the systems community, they write papers like GFS and Bigtable that are about like building big systems, but maybe not so much about building nice APIs or programming models necessarily. I don't mean that pejoratively, it's just not their domain. And then the database community, I think, traditionally has thought more about those sorts of things. Like it comes more from, I don't know, the history of that community has more to do with supporting a programming model that is appealing to developers. And this is one of the few examples at Google of a project that really went big on both of those fronts. And I think it's actually a big challenge to do organizationally as well as technically. And one of the other things about this, which I noticed when I was trying to just figure out what order to put the slides in, this whole thing, there's a lot of stuff about Paxos, there's a lot of stuff about this true time concept, there's a lot of like weird organizational thing around these things called directories and many other concepts, and they all depend on each other. Like the division, the layers in the system aren't layers. It's just everything is like this sort of muddled mess, which is actually a feature in the sense that that's necessary for performance. And if you read the paper, there are examples of situations that say, well, actually, it's not quite like that. Really, you kind of need to have a cache here that has this thing that's actually from the interior of the Paxos transaction. You need to grab that timestamp and take it out of Paxos and use it in order to make sure that the snapshot read is efficient. And things like that kind of violate encapsulation. What they're basically doing is violating the encapsulation of these nice systems concepts and using that to create this system that actually behaves in a way that people would want to use. It's worth mentioning the people on this project were just astonishingly good, and they rewrote this thing many times, and they took 5 years to do it, which is kind of a long time if you consider who was working on this thing. It's really the Larry Birds and Magic Johnsons of Google were working on this for a really long time, and I don't know, I mean, of course they can't talk, that's not something you would mention in the paper, but I think it's worth mentioning. I think one of the reasons I'm so curious about it is just it took them so long to get this design right, and that it's a very subtle thing. And initially they were going to do a lot of things that seemed really cool and ambitious, but they didn't do them. It was just too hard. Like they were going to support different types of consistency, and they just abandoned that. And then they were going to support automatic, balancing of data, and they abandoned that too. It's just very difficult. All right, so I'm going to talk about the programming model in a little bit, but this is sort of like the blue pill, like the kind of cold reality of what's underneath this. I realize it's a little hard to read, but basically there's this global thing. Do I have a mouse pointer somewhere? Oh, here it is. There's this universe master, which is effectively global, which I believe just keeps, they're pretty vague about it, but I think it just keeps track of what all the zones are, and that sort of global configuration doesn't handle a lot of load. There's a placement driver, which is responsible for rebalancing things globally. And then there are these zones. And a zone is sort of like a Bigtable cell, if you're familiar with Bigtable. And inside a zone is where all the really intense stuff is happening. There's a zone master. There are these location proxies, which are basically caches, I think. And then a lot more than 3 span servers. So the span server is the thing that really fans out in the spanner architecture. And in a large cell, there would be a lot of them, like thousands, that sort of thing. There's also this other way of thinking about the system, which is, this is a diagram, all these diagrams I just copy pasted out of the paper, but this diagram is more about the participants in a transaction in Spanner. And I'm not going to just go through and describe every piece of it, but the gist of it is that I hope, most of you, is anyone, what's a good way of saying this so people will actually raise their hand? Who is familiar with like HBase or Bigtable or Cassandra or something like that? Okay, great. So that helps a lot. So, these systems are divided into little tablets. Each tablet, there are tablets in Spanner as well, are just key value maps. And they run Paxos between all the replicas of a tablet. So anything that happens to a tablet, any write that happens to a tablet will go through Paxos. And I hope people are familiar with that, or I might have to explain a lot of stuff. But Paxos is basically a way for multiple participants to agree on something, and namely a leader. And so what ends up happening is that these tablets are independently running Paxos. So Paxos is not at the level of a span server, it's actually at the level of a tablet, and that's very important, and is taken advantage of numerous times in the paper. At one point we're going to have even more Paxos groups, and the paper mentions that they had to abandon that design because it was just too complex, which makes a lot of sense. I mean, this ended up being pretty complicated as well. The reason this is a diagram of a transaction instead of a Paxos group is that the leader of the Paxos leader for any particular tablet and spanner may also be a participant leader or not. It could be like a participant. It could, well, whatever. The point is that if there's a transaction, there are many participants in the transaction, and they all have to collaborate. So this kind of shows you, the reason I like this diagram is that it shows you all of the arrows where data can be flowing or information can be flowing during a distributed transaction in Spanner. And there are many of them. And of course, in either direction, there are just a bunch more things. And there's also another level of leadership at the transaction level. There are participants and also coordinators. So you have like multiple levels in different axes of coordination and mastership, and all of them use true time to decide about when things are happening. So this is also perhaps a little too small to read, depending on how good your eyesight is, but the interesting thing about spanner tables, and I think this is actually a really cool idea. I mean, for most people doing relational databases in practice, you really have a hierarchy, right? You'll have your customer table, your users table, and then you'll have all of their posts, and then underneath that you'll have, all the things that the post depends on or whatever. And it ends up forming this nice hierarchy. Occasionally you have like real relations and graphs and stuff like that, of course, but at the core it's often possible to model your data just as a tree, and Spanner takes advantage of that. And what you do is, so every row in Spanner is part of some directory, and a directory is one row, and it starts off with one row in a table that's defined as a directory table. So in the example in the Spanner paper, there's users with photo albums. And so the users table is considered a directory table, which means it's at the top level and has no parent. And then the albums table is beneath this directory table and has this keyword interleaved, which basically means that Spanner as an optimization, this doesn't semantically affect anything really, it's just an optimization, but it will layer the albums within the same, hopefully the same tablets as the users. So if you need to operate on both of those and do some kind of join, you have a good shot at spatial locality, which is an incredibly important optimization. And this is not coincidentally the same way that the ads database is structured. I don't think that's some kind of crazy PII. That's not some crazy company secret or something. That it's sharded by customer, and yes, so this is a really important property for performance, and I think I like the idea a lot personally of modeling SQL tables as a hierarchy, and this idea is also present in the Megastore system. The replication config is also per directory, which is very powerful. So you can have individual users can have different replication configs. Namely, if you have a user in Europe, you can say, I want their, I want the read-write replica to be in Europe. If you have a user in America, you can do the same thing in America, and so on and so forth. And this is, I think, pretty profound to have operational control at that level of granularity rather than at the level of like the entire users table or whatever, which is more typical for a system like this that does global replication. And I also think it's pretty impressive that Spanner and that placement driver stuff I think is responsible for this. It will actually move directories in this sense of the word directory close to other directories that are co-accessed. So if you have two directories that are used in tandem frequently, Spanner will eventually move them closer together physically and get them to be in the same Paxos groups and stuff like that, which is I think a pretty interesting and difficult feature to implement. One thing that they talk about all this and you're like, wow, this is really complicated. And then they say, oh, and by the way, it's actually a lot more complicated because if a directory is too big to fit on one machine, we split them into fragments. And everything you've been thinking about as being atomic to a directory is actually atomic to a fragment. And then we just do a lot more work to make that work from a practical standpoint. I think there is a requirement still that they don't discuss in the paper, but I think it's a practical requirement that a single row, not a directory, but a single row has to fit in memory in one machine. And if it doesn't, horrible things happen. And that was certainly the case with Bigtable. So I don't think they split below that, but they'll split directories as needed, which is, it must be a nightmare. Just, I don't know. Every time I think about what they had to do to implement this, I'm like, I'm really glad I wasn't doing that. So TrueTime. I'm going to talk about TrueTime, first of all, at an intuitive level. I have a picture of a globe here, which represents global time, and it has GPS satellites around it. So Spanner is all about this idea that there is such a thing as a global clock. What's important to realize, and they don't really underline this in the paper, is that there is no such thing. I mean, everything is just approximating it, and the key about TrueTime is that it doesn't return times, it returns intervals. And I'll talk about this later, but ultimately, the thing that makes Spanner work is it just sleeps. When it doesn't have enough certainty, it just waits until it does, which is sort of cool, but also really slow. So, this is an issue, right? It's like they call clock uncertainty epsilon in the paper, and as that number goes up, Spanner performance goes way, way, way down. And they talk in the future work about how they can get it down to under a millisecond in general, but that's not necessarily always the case, and it is the big caveat to all the true time stuff, is that the solution always, at least if you're dealing with timestamps around now, is to sleep. And so you really want the epsilon number to be low, and you want to have your network be really fast and things like that. I decided to make a diagram. The paper diagram, actually, I don't think they have a diagram in the paper. The diagram in the OSDI talk, I don't like the colors, so I made my own. and then I got carried away. So this is a computer in a data center somewhere from 1983 or something. And its idea of now is right here. So, and by now, I mean if you call like time null in C or whatever, like now. And it also has this value epsilon, which I'll discuss more in the next slide, which is its local to the machine notion of what its uncertainty is relative to what it thinks the global clock is. The global clock may actually say now is over here. That's totally fine. The only thing that's really bad is that if the global clock goes beyond one of these TT now latest or TT now earliest brackets, terrible, terrible, terrible things happen. And epsilon moves in such a way that that's quite unlikely to take place, but it would be fairly catastrophic. If this thing moves over here, then like it's bad, right? This is what you really don't want to have happen. I would say, having read the paper pretty carefully around this, it's probably not going to happen. The way they deal with this is that epsilon, which again is per clock / per machine, is managed by a special daemon that runs, presumably as root or something like that, doesn't matter. It runs on every machine. And what it's doing is pinging multiple time masters, which are special machines running in Google's data centers that either have a GPS clock on board and or an atomic clock on board. And there are many of them per data center. It contacts as many of them as it can locally, as well as multiple time servers in other data centers, just in case something really bad happens. I don't know what would happen, that the time masters would go down, but the machine itself wouldn't go down, but they've accounted for that. And the epsilon is defined as basically the NTP lag. I mean, that's not what they call it, but that's what it is. So it starts off with whatever the lag is between it and its nearest time master. And they add to that the delta time since the last successful update with the time master. So that's to say that how long has it been since I knew how far off I was based on just ping times. And they multiply that delta t times what I'll just call k paranoia, which is just this like pretty high number representing the kind of average amount of, not average, like absolute worst case amount of clock skew per second for any machine running in Google's data centers. And the concern that you might have is, well, what if the clock is like really, really broken? And they make the observation that for a clock to be that broken, and there are studies of Google's telemetry data, it would, they find 6 times as many CPUs that are broken in a catastrophic way than clocks that are broken that way. And of course, a bad CPU is probably considerably worse than a bad clock. Well, that you could argue that, but nevertheless, that's what they say. I want to diverge from the topic for a moment and say one of my favorite memories from Google was they had this global telemetry monitoring of every machine at Google, not a big surprise, and they were monitoring, among everything else, the number of ECC error corrections that had happened as a time series, and it just like hovered near 0 globally. And then there are these weird moments when it would not hover near 0 and it would like spike globally, like all over the place. And they could not find any kind of event that would explain this throughout any of Google's infrastructure. And they really wanted to get to the bottom of it because this is unnerving, obviously. You don't want to see ECC2, you don't want to see ECC errors spiking. And finally someone realized, they looked up some astronomical database, and there are sunspots. So every time there's a sunspot, we'd have these spikes of ECC errors globally. Like they'd have like 15 instead of 0. It wasn't very many, but it was really interesting. So they said they'd build the world's most expensive sunspot detectors. Anyway, all right. So this is the point in the preparation for this talk where I was looking at this slide. I'm like, okay, I kind of understand this, but I don't think I can explain this, in the time allotted. So beta option 1 was to explain it, which is, we can do that if you guys want. And meta option 2 is to provide a nice hyperlink to the exact moment in the Spanner presentation where Wilson beautifully explicates what's happening. And I thought that was probably a better bet. I will describe a few important aspects of this slide, which is obviously like kind of too small to read, but the whole point is that you shouldn't try to read it right now. I'm just going to tell you a few important things that you will learn when you study it carefully or watch Wilson explain it. There's a step here, compute overall S, which is basically for a transaction, distributed transaction, what timestamp are we actually going to assign to this transaction? So there's a collaboration that takes place between the participants in the transaction to decide what that value should be. And once they've decided it, it's committed. And after they do that, there's this thing called commit, wait, done. So this period between these two things is sleeping. That's what's happening. And the issue of Spanner always is just, how long is that interval and how much work can you get done in parallel while it's happening? Often quite a bit, so it doesn't end up being that much of an issue. But it's important to kind of understand and look for that in these timing diagrams, and there are many of them in the slides for the OSDI paper presentation. Also, in the transactions, it's interesting, it can be kind of confusing reading the paper that there are many different things called S, but they don't differentiate between them, but they come from different places and they mean different things. And especially in the context of these distributed transactions, the S's that are intermediate are not the one that's actually committed. The transaction will have a single timestamp, not lots of intermediate timestamps. What's happening here is each line here is a participant in this transaction. Well, this is actually the coordinator, and these two are the participants. But each participant chooses its own S. It sends them up to the coordinator, which decides on a final S value. I think it might have been a little clearer if these S's had subscripts or something like that. But rest assured, the transaction does have a specific timestamp, which is very important for the correct functioning of the rest of the system. And it's also important to realize, I'll go back to my, to this slide. What typically happens is that you need to grab blocks on a table. You'll do that. Then you call TT_now, and you basically do all the work you need to do with the locks. Once you're done, you figure out, this is difficult to explain this diagram. I realize you're not going to understand this if I do this a better diagram. The gist of it is that you always wait long enough that no one external to you will be confused by your timestamp before you release the locks. That's the gist of it. So basically, anytime you hold a lock, it's always, a lock not in a local sense, but in the sense of a table lock in Spanner. It's very important that you wait until the true time earliest value for your now timestamp has passed by, and then you can release them. And the paper is actually pretty clear about that. So, all right. This is a table from the paper. I'm not going to go into great detail about this, but it is just worth mentioning that there are several different types of operations in Spanner. Read-write transactions, of course, do require locking, and you need to talk to the leader in a replica group. It's also worth mentioning that transactions, when they're read-write, if you perform a write and then read from it later in that transaction, you won't be able to observe the write. So the write isn't visible even within the transaction until after the commit has happened, which is a little bit different than what you might expect in a traditional RDBMS system. Read-only transactions and snapshot reads are quite similar. The main difference is that read-only transactions, you provide more context as a client of Spanner about what you're actually going to be reading from, and it ends up being more efficient in the aggregate once you're done, and you can also have better guarantees that everything is actually part of a single snapshot of the database. One of the really cool things about Spanner is that unless you're trying to read from the bleeding edge, if you're even willing to say, I'm willing to, when you perform a read, you can say, I just need this to be less than an hour old. it will almost never block. I mean, unless one of the participants is way, way, way behind in a replica group, in a Paxos group, you'll almost always be able to get that data in a way that's globally consistent with essentially no locking, which is awesome, an awesome property, which is great, especially for things like MapReduces and stuff. I have to say that I think there's a bug in the paper. I think 0 there should say non-zero, and they refer to section 413, and I kept on reading that. I sent a note to my friend Wilson, the guy who's smarter than me. I sent a note to him because he would talk to me sometimes when he worked in New York, and I asked him about this, but I sent it this afternoon. I think he probably was living his life and didn't want to respond to my email. Let's see if he's responded so far. Nope, still hasn't responded. Anyway, I'm probably wrong. It's probably totally correct, but I hope that no one watches this video if that's the case. There are some interesting measurements. I like that they actually publish this. Some things, sometimes Google papers are a little irritating because they talk about the ideas, but they don't want to give too much information about systems themselves, and so they elide a lot of the gory details. But I don't know. I'm not going to read them out loud or anything. But the gist of it is that the two-phase commit is pretty scalable, up to like 10, 25 participants. It starts to degrade after 50. Well, now you know. Don't do a two-phase commit with 200 participants. And the thing on the right is actually a very interesting result in my mind. It's basically saying what they do in this experiment. Oh gosh, I think I should have speaker notes, and I don't, but I believe they had 25 span servers in this thing. They're just like hammering on it. And they have replicas in 3 different zones. And then in 2 of the groups, in 2 of the situations, the red, what we're seeing here is the cumulative reads completed. So basically, you just get to see what the throughput is the derivative of this thing you're seeing. So for if they kill a non-leader of the zone of the Paxos groups involved in these replication configurations, they kill all the non-leaders. Nothing happens. Like the throughput just sails right through, which is neat. What's even neater is that if they politely kill the leaders of those groups, which is to say, I'm going to kill you, please offload your leadership responsibilities, and then they wait 20 seconds and then kill it. Also, there's no effect on throughput, which is, again, is impressive. And even in the case where they're not very polite and they just kill -9 the leaders of these groups, what ends up happening is there's an initial period of 0 delta throughput as the system struggles with the fact that it needs to bring up new leaders and so on and so forth. But the queuing is sufficient, and the fact that everything becomes underloaded for a little while and has extra capacity allows the system to actually completely catch up to where it would have been, which is remarkable. So it's not just that it would be unsurprising if the slope actually was, if the blue line was parallel, but essentially underneath the other 2. But it's neat that it actually catches up to where it would have been. That's a pretty impressive result as well in terms of their ability to recover from unplanned failures. And that failure scenario isn't that unusual. If you had a network partition that if an entire data center just immediately in an instant went dark, this is what would happen from a schematic standpoint. They also have some measurements of true time. The gist of it is not terribly surprising. The epsilon, the error from the global clock, is generally what you'd expect it to be in a network that has really nice routers, which is what they have. They have an example here in Wilson's talk. Someone asked a question about this. Basically, this was an event where the local time masters, for some reason, went offline. I don't know why, and the local machines had to talk to remote time masters instead. So rather than being sub-millisecond distance, they were now 4 or 5 milliseconds away in nearby data centers, and the system will slow down, but nothing breaks. The crazy mushroom cloud doesn't happen, and true time works. The true time piece of this, I have to admit, I think it's a really cool abstraction, but the implementation is not, it doesn't seem very complicated to me. Maybe I might be missing something, but it's mostly just the concept, and the implications for the spanner code base is really intense. But the actual architecture of this kind of NTP syncing thing didn't seem very complex to me. I'm getting towards the end of this. I hope I'm not going too fast. Does that ever happen? Okay, good. So there's like this incredible bit in the paper where they talk about, well, we were going to figure out how to move data automatically in response to, changing load or data center weather or whatever. And I think they're very polite when they said, well, we could do that, but there are troubles with orchestration of the remainder of the application code that needs to move with the data. And this has been this continuous problem for Google, and I'm sure many other companies that are dealing with data that has to live in multiple places. And namely, with Bigtable, they had this idea of coprocessors, which were really cool. The idea was that you would write code that got the privilege of running. It was, basically C code that got to run on the same machines that your actual data was stored, and you would have the opportunity to kind of grab a lock and operate on the underlying Bigtable data from the actual local host, even though someone else is running the Bigtable cell for you. It was a really cool idea, and my project, Monarch, bet really big on this, and it was extremely difficult to use operationally just because of the nature of running a service like that. Getting isolation in a multi-tenant service to work with coprocessors had lots of caveats and was very complex. And so that idea was, and what you could actually do was limited. I mean, you couldn't do anything global in a coprocessor because it was necessarily restricted to its local tablets and, other issues like that. So people ended up just doing what they'd been doing all the time, which is just trying to get their application code to run in the same physical, in the same, have the same LAN essentially as their Bigtable, that's not the right terminology, but that's the idea. And the trouble is just that even if we can get the data to move, the scheduling stuff at Google is so unbelievably broke and complicated that we'll never be able to get the application code to move in a elegant way along with the data, and it's a shame. It would be a real ocean boiling thing to solve that, and there have been some really great people who've spent many, many, many years toiling over that problem, and I'm waiting to find someone who figures it out. Maybe someone will be able to do it with containers or something. They'll be able to snapshot that and live migrate containers with the same IP address or something, but this is a really thorny problem. And the other thing that's interesting to me is just this, the pendulum is swinging back to SQL-like behaviors, which I think is actually a really good thing for application programmers. And they were mentioning that at the underlying level of a single span or tablet server, they are still using a key value store for everything, yet the queries that are coming in are basically SQL queries, and they just need to swap out all their internals to be more SQL-y. And I'm excited to see what they're able to come up with that too. It'll be a lot of work, but it's mostly local and should yield much faster read behaviors for many things in Spanner. Okay, so I think that's it. The thing in the corner that I'm sure you're straining to read says, also come talk with me about my awesome company. So I'll take some questions, but I'm always love talking with people about what we're doing, and it's pretty interesting and early. And I'm happy to talk about it. I don't really believe in stealth mode. Go for it.
Wait, do you want to say anything else about your awesome company, or?
No, we're all going to be. We're all just trying to decide what yacht we want to buy when we IPO, and it's going to be great.
Okay, all right.
Yeah.
Good. I just wanted to make sure that you had the space for that.
No, I don't want to. This is not a paid advertisement. But I do want people to talk to me about it.
Yeah. All right.
Oh, thank you.
Hi. Good talk. I have a couple of quick questions. So the first question is there a benchmarking or consistency verification mechanism in place that makes sure that external consistency is actually works, doesn't have bugs in the implementation?
I mean, of course, I can't definitively answer that, but my sense, someone asked a similar question at the OSDI talk, and the answer is basically no. I mean, I think that from a theoretical standpoint, it's pretty solid, and there's two types of things that could happen. One is that there's a logic error in Spanner, which of course is possible. I'm sure they've tested it into oblivion as far as this stuff goes, because this is really important. And the other issue is that a clock will actually get so far off that it exceeds epsilon in terms of its deviation from global clocks, and in that instance, and the paper does describe some heuristics they have, like if things are way too far off, it just kind of, it just silences itself and takes itself out of rotation. But if one of those things wasn't caught, of course it's possible. And so that's really, I think, the biggest theoretical vulnerability is that a local clock would deviate by more than epsilon. And Wilson's answer to that question that was asked at OSDI, which I guess I'll just parrot since, he is the right person to ask, not me, was that they'd be 6 times as worried about bad CPUs. And so kind of by definition, no, I guess.
Quick second question. Second question, regarding geodistribution, was it just a simple majority in place? For instance, like 3 replicas in a data center, 2 in another data center. How do you manage majority in a Paxos group like that?
I don't know the exact answer to that, but my guess, just given what I think most people know about Paxos, is that it should be an odd number of replicas. But I do know the replication configuration is quite flexible. I mean, you can have a single user could be replicated in 5 places, and a different user could be replicated in 3, and so on and so forth. And they do talk a little bit about the trade-offs. Like the ads database, all the replicas are actually in the United States because there are some pretty substantial latency trade-offs. If you put replicas far from each other in the network, then everyday writes can take a long time for Paxos to agree upon and stuff like that.
I'm curious whether the idea of breaking directories into fragments came initially, or was it like a V2? V1.1?
My guess is that was actually initial because Bigtable has always had problems with large rows. It's just an operational problem with Bigtable that if your row gets too big, you can have this row of death. Like, it's a bummer if a single server in Bigtable will die. What's a really big bummer is if you have a row of death that's so big that it kills the tablet server it's on. So it kills it, and then Bigtable, naively assigns it to another tablet server, which it then kills. And then it assigns it to another tablet server, which it then kills. And then suddenly you're like, why are half my tablet servers down or like in a crash loop? And then you find this bad tablet. And of course, they wrote code to be more intelligent about that and to quarantine them, at which point your reads no longer work and your MapReduce hangs because there's a big row. So like they'd been dealing with that problem forever, and that team had been probably sufficiently traumatized. I mean, the Spanner team is really the same thing as the Bigtable team in terms of the people who designed it. I mean, the teams are both very large, but the designers were in common. So I'm quite certain that they knew that directories were going to have to be split into fragments, but I think when they got into writing the paper, it just made it too complicated.
Ben, nice talk, thank you.
Thank you.
You showed some data with your epsilon window being 10 milliseconds, but if I remember reading the paper correctly, that corresponded to about 2,200 kilometers difference between the data centers.
Oh, really?
And I checked this last night.
Interesting.
But there's like 20,000 kilometers and a half circumference around the world. Does that mean your epsilon's going to be 10 times that if you were talking to this side of the world?
Well, I think that, I see what you're saying. I think what you just experienced is how bad I am at kilometers. Yeah, so 2,200 kilometers, that's like 5 miles or something. No, I'm just kidding. So how far so I think that, sorry, Americans.
So 2,200 kilometers is about 11 milliseconds.
Right, that makes sense. Well, what I was going to say is that I think the way they set it up is that you speak to all of the time masters in your local data center, and then I guess you preferentially choose time masters that are in data centers that are close to you. So you just wouldn't choose the one that was 20,000 kilometers away. And if you did, your lag would be considerably worse than that. Is that answering your question?
My question is more like, what would be the expected update latency if you had updates from 2 sides of the world?
Oh, I see what you're saying. So if you had to sync with a time master that was in the worst case, across the world from you, well, I mean the ping times for like transatlantic stuff are considerably larger. I'm kind of having this like weird paranoia about confidentiality at Google right now about like being too specific, but I mean it's definitely more than 5 milliseconds. But it kind of gets down to just what that ping time is, and let's say it's an order of magnitude higher. But I don't know if that helps.
Thank you.
You're welcome.
Questions on this side? Oh, shit. Okay. Are you sure nobody on this side? I'm going to go to the other side, and then we're going to be... Another one, Paul? Okay, okay. I will come back to you then. Who was... Oh, you.
I think there's probably slight confusion there. I think you can commit at 2 replicas across the world with only syncing with your like local time masters, right? So like you can feasibly commit like I mean, actually I think that's one of the really cool things about the true time stuff is that you can actually like do a distributed transaction.
Oh yeah. No,
like,
I misunderstood. I thought you were suggesting just determining epsilon. Yeah,
I mean, like
he's right.
Catastrophically, like if like all the time masters went down, then that might happen. But I guess it's like a super rare event.
Yeah. The idea is that all the various participants have pretty low epsilon because their local time master has what's considered to be a correct clock, you know, and that it's using GPS or atomic clocks or both or whatever. Maybe that helps, but you're locally syncing to something that's very close to correct. So everyone's able to express pretty low uncertainty about timestamps when they're performing these commits.
So is this the database of choice for all Google projects going forward? What are reasons people don't choose this for something else?
Well, in full disclosure, I left the company a couple of years ago, so I mean, I can't say for sure, but my guess is that people are, it's not, I mean, there's always a trade-off with all these things, right? And it's like if you didn't need a lot of these features, I think, for instance, if you really just needed a key value store, you'd be better off with Bigtable. It's much faster. I mean, the throughput you can get from Bigtable is still considerably larger than what you can get with Spanner, and the latency is also lower. But I think if you were using Megastore right now, my suspicion is that there is a migration path to Spanner being planned, which is a lot of applications at Google are using Megastore because they want those sorts of SQL-like behaviors. So I think those projects probably are in the process of planning migrations or performing them, but I really can't specify because I just don't know.
All right, I'm on this side again. Paul?
I guess my last question is, how often have you experienced the maximum drift on some of the hardware clocks being anomalous outside of your bounds of expectation?
It sounded from the paper, and again, you know, I can't say for sure, but it sounded from the paper that that kind of never happens. I think that was why that's the idea, was that it's. I thought about on the slide where it shows the bounds of having like a distribution to show just how many sigmas you are from what they think is reasonable. But I remember reading the paper that it sounded like the K-paranoia that I wrote, that was my term obviously, but I think that number is really paranoid. Like they really, really don't want that to happen. So the idea is that you're pinging the time master frequently enough that you don't really care about that constant. But if you were to not be able to be in touch with your time master for a long time, I think it's very aggressive about how bad it assumes your clock to actually be. So I think it sounds like they don't have any knowledge of a situation where they got bitten by that.
Thank you.
You're welcome.
All right, this side? No? Okay. Thank you so much.
Thank you so much.